Hello students, welcome to class 12 physics class. Today we discuss a last part of this chapter ray optics, that is optical instruments. So in optical instrument we discuss about the microscope and telescope. Microscope, the simple microscope, compound microscope, and telescope only the astronomical telescope, refracting and reflecting types, and their magnifying power expression derivation is not there, but still I will give the derivation also, otherwise you cannot understand. So first let we start with a simple microscope. We know that the simple microscope, it is the first microscope, it is discovered in here. For simple microscope, that means it is a magnifying glass. Simply it is called that magnifying glass. It is just a convex lens of short focal length, and if we held very close to the eye, we can see the letters or every object larger, the larger image of the object. Okay, so we discuss the working principle and its magnifying power at a least distance of distinct vision and at infinity, at infinity also. So this is the ray diagram for the simple microscope. Here you see that when the AB is an object, it is placed between the focus and the optical center of a convex lens, and we know that if the object is placed in case of a convex lens, it is in between focus and the optical center, then it will form a virtual erect and magnified image of that object. So here A dash and B dash is formed on the same side of the lens of that object. It is an image of the object AB. A dash and B dash, it is the larger image. Since the normal eye, we can see the object clearly at a distance of least distance of distinct vision. That is, we know that that is a 25 centimeter. Where we did not give any pressure on our eyes or any stress on our eyes, we can clearly we can see the image without any pressure. That is called least distance of distinct vision. So in that vision, what is the expression of the magnifying power whenever the final image is formed at that distance? And this distance is denoted by capital D, as shown in this figure. This distance of distinct vision is denoted by D. The position of lens is, if we adjust that, the we can adjust these things, the position of the lens, so that the image will form at a distance of D from the lens. And this is a ray diagram for simple microscope. Now we calculate the magnifying power of simple microscope. So magnifying power of a simple microscope, it is defined as the ratio of the angle sustained by the image and the object at the eye when both are at the least distance of distinct vision from the eye. Both at the least distance of distinct vision. Okay, the angle formed by the image and the object with the eye, at the eye when both are placed at the least distance of distant vision. Now from this figure we see that the eye is held very close to the lens, and so the angle subtended at the lens, it taken to be the angle subtended by the eye, because the position of the eye is very close to the lens. So we can say that the whatever the angle made by the lens, that is the angle subtended by the eye. The image A dash B dash is formed at a least distance of distinct vision, that is D. So we can say that the angle A dash O B dash, that is equals to, here you see that I will enlarge the diagram. See, A dash O B dash, that is equals to beta. Okay. And we imagine that the object AB is displaced from its position to the position A double dash B. that is a it will displace from its position. So whatever the position from A to A dash, that will be the position of displace a object, displacing of the object AB, A double dash B dash, A double dash B dash at a distance of list D, because we need the angle, both the angle subtended by the image and subtended by the object at a distance of least distance, distance vision. That's why we shift the object position at a distance of D, and that is denoted by A double dash B. A double dash B dash is represent the object, and A dash B dash will be the image. So the angle A dash O B dash, that is equals to beta. So angle A double dash O B dash, that is equals to alpha. This will be the angle subtended by the object alpha, and the beta one, the angle subtended by the image. So m equals to what we can write, beta by alpha, okay, because this alpha and beta, that is equals to, because from that definition, angle subtended by the image at a least distance of distinct vision divided by angle subtended by an object at the least distance of distant vision. So we can write m equals to beta by alpha. Because these two angles are very small, that's why we can represent it by tan beta by tan alpha. So from first angle, that is angle from, or the from triangle A dash O B dash. So tan beta equals to what we can write, and tan alpha equals to what we can write. From the triangles, from in place of tan beta and tan alpha equals to what we can write, tan beta equals to, from the triangle AOB, AOB, we can write AB by OB, that is from tan beta. AB, not the from the larger triangle A dash OB, not that one, small triangle, that is ABO, that triangle, tan beta equals to, we can write AB by OB, and tan alpha equals to, we can write A double dash B dash by OB dash, A double dash B dash by OB dash. Okay, now because A double dash B dash equals to also the same height of an object, so in place of that we can write AB. Here you see that this one, A double dash B dash equals to AB. So if we put it over there, AB cancel, we have OB dash by OB. So OB dash, that is the distance vision of this distance of distance vision, that is D. And because of the convex lens, we use the negative sign, and divided by OB. OB is the object distance, OB is the object distance, that is x. So it is also be a negative sign. So m equals to, we get d by x, m equals to, we get d by x. Okay. Now, if we consider the f be the focal length of the lens, so the image will be formed at a distance of distant vision. So that means the value of d, that is equals to v. This gives us the image distance, v equals to minus d, because virtual image is formed in case of a convex lens. So if we use the lens formula 1 by v minus 1 by u, that is equals to 1 by f, and if we put the values over there, in place of v if we put minus d, in place of u if we put minus x, so we get m equals to 1 plus d by f, 1 plus dy. After solving, we get m equals to 1 plus d by f. So from here we can see, we can conclude that if the lens, if the convex lens has a shorter focal length, they have the greater magnifying power. So the magnifying power and the focal length are inversely proportional to each other. If the focal length is increases, magnifying power will be decreases. So, we use for making simple microscope the convex lens having short focal length. That's why if the short focal length will be there, then the magnifying power of that microscope, it will be greater. This is at the distance of distant vision. And this is the diagram when the final image is formed at the infinity. not the least distance of this in distant vision. No D is there. Okay. So then what will be the and this is the angle formed by the object at a distance of distant vision D, and the image is formed at the infinity. I will be focused at infinity. And when we get the image at infinity, when the object is placed at focus. So in this figure, the object is placed at a focus. That's why the image will formed at infinity. Clear? So the magnifying power, it is also same. It is defined as the ratio of the angle formed by the image when it is situated at infinity at the eye to the angle formed by the object at the eye when situated at a least distance of distant vision. So no D, not only no D is there, not that purpose. That means that in previous case in place of V, that object distance is denoted by minus D. It's denoted because the image is formed at this distance. But here the final image is formed at infinity. That means the object position will be different. For this case, the object will formed at focus, and the previous one, the object will placed in between focus and optical center. So for making the for getting a final image at infinity, we have to put the object at focus, and the definition of magnifying power will be same. The ratio of the angle formed by the image at the eye to the angle formed by the object at the eye when it is situated at a less distance of distant vision. That means m equals to tan beta by tan alpha. So tan beta equals to h by f. From this diagram you can see tan beta equals to h by f and tan alpha equals to h by d. Okay. So if we put over there, we get m equals to d by f. So this is the magnification of simple microscope when the final image is formed at infinity. So this magnification is one less than the magnification when the image is formed at the near point. Okay, so by viewing is more comfortable when the eye is focused at infinity. And where we use this simple microscope, the for jewelry, watchmaker use the magnifying glass having the magnified view of the small parts of the watches or the fine jewelry look, and the magnifying glass is used in science laboratories for reading vernier scales, etc. In many purposes it will be used. Simple, but not so wide purpose. Okay, its use purpose also be limited. So using this formula, some numericals will come and you use the uh, concept of the lens, the magnification sign convention, that things, and you solve the numericals. One numerical example I will give here. Try to in your home. If you have any problem, I will discuss in that later. So just try it. You just read this question and the solution, you just go through its solution. If any line, if you have any problem, let me know, write in the comment box. So in the next one video I will make for this numericals only. Okay, now let's come to the next microscope, that is compound microscope. So some drawbacks also be present each and every instrument. There is also some drawbacks in a simple microscope. We cannot use in the wider purposes. That's why we invented the compound microscope. So a compound microscope, it is an optical device. It is used to see magnified images of tiny object. A good quality compound microscope and can be produced the magnification or of the order of 1000, 10 to the power 3. Okay, construction, this compound microscope also be constructed with a convex lens, but here we use two convex lens of short focal length. One lens which is placed very close to the object having small aperture and the short focal length, that is called objective lens, and another one convex lens which having short focal length but the larger aperture. But short focal length in means that its focal length is greater than the objective lens. Objective lens focal, whatever the objective lens focal length, this lens will be greater than that one. Okay, and it is placed very close to the eye of the viewer. That's why this is called eyepiece or ocular lens. So one is a objective lens, another one is a eyepiece or eye lens. So the distance between two lenses can be varied by using rack and pinion and arrangement. When it will be made, we can arrange like this way. Here also we find out the magnification expression when the image is formed at least distance of distant vision and at infinity. This is a diagram where the image is formed at a least distance of distant vision, that is at a distance of d. So here you see that first lens which having small apertures and small focal length, that is objective lens, and the second length which aperture is larger and focal length is greater than the objective focal length, that is the eyepiece which is placed close to the viewer's eyes. So the object here, the object AB to be viewed in place of distance u. U is the object distance, slightly larger than the focal length f0. In this figure, you can see that slightly larger than the focal length f0 of the objective O. The objective forms the real, inverted and magnified image A dash B dash of the object AB. In this figure, first through the convex lens, it will be formed a real, inverted and magnified image of an object AB. A dash B dash will be the magnified image of an object AB as shown in this figure. The separation between the objective and the eyepiece is so adjusted that the A dash B dash, the image lies within the focal length of eyepiece, that is within FE. In this figure you see that the image will lies within the focal length of eyepiece, that is FE. We can adjust it like this way. The image A dash B dash for the second eyepiece, this image A dash B dash acts as an object for eyepiece which essentially acts like a simple microscope. The second part, the eyepiece, will behave as a simple microscope. First case, here in simple microscope we place the object in between focus and the optical center. Here you see that this image A dash B dash will be placed in between the focal length of the eyepiece and the optical center of the eyepiece. So we can say that this portion, the second part of this compound microscope, will behave as a simple microscope. So whenever we find out the magnifying power of a compound microscope, we first find out the magnifying power of an objective lens, then the eye lens. The eye lens, that is the magnifying power of the simple microscope, that one we use because it behaves as a simple microscope. So the eyepiece forms a virtual magnified final image, that is A double dash B double dash is inverted with respect to the object AB. Actually, if we see the object, if we consider the object A dash B dash, so same side of the object, but with respect to the main object AB, it will be inverted. Otherwise, with respect to A dash B dash, A double dash B double dash is the virtual and erect image and a magnified image. Clear? So let's we find out the magnifying power. Magnifying power of a compound microscope is defined as the ratio of the angle sustained by the eye at the final virtual image to the angle subtended by the at the eye by the object when both are at least distance of distant vision. That means m equals to, we can write beta by alpha, beta by alpha. Okay. Hmm. So first of all, we find out the magnification due to the objective lens. So magnification, total magnification of the compound microscope, that is m equals to m0 into me. Using that concept that m equals to beta by alpha, if we use the tan beta tan alpha, if we use the expression over there, we get h dash by h into d by ue, that is a m0 and me. Okay, that's why we prove it individually. First, the magnification due to the objective lens m0, that is equals to height of the image by height of the object, h dash by h. In this figure, we notice that tan beta, tan beta equals to what we can write? Tan beta, tan beta equals to, we can write h by f0, h by f0. Okay. So h by f0, that is equals to, we can write h dash by l, h dash by l. L is the length of the microscope tube or the distance between the two lenses, h dash by l. So h dash by h equals to, that is equals to l by f0, h dash by h, that is equals to l by f0. So we get m0 equals to l by f0. We get m0 equals to l by f0. So l is the length of the microscope tube or the distance between the two lenses. Okay, this is the magnification of objective lens. Now magnification of the eyepiece, because it behaves as a simple microscope, already we find out the simple microscope magnification power, that is 1 plus d by fe, f 1 by 1 plus d by f, but here due to the eyepiece, that's why the focal length is the eyepiece focal length. So 1 plus d by fe. D by ue, here we use the lens formula 1 by v minus 1 by u equals to 1 by f. So we get 1 plus d by fe. So the total magnification, that is m equals to m0 into me. So now we put the values over there, we get l by f0 into 1 plus d by fe. From here you see that this is the required magnification at the least distance of distance vision, and we see that the focal length are in right in a denominator. Okay, so if the focal length is short, then magnifying power will be greater. Now when the final image is at infinity, so just the expression in a me 1 plus, that will be the different, already we discussed infinity, that means the a dash b dash, the image of the first image formed by the first convex lens, that is lie in on the focus, not within the focus and the optical center of the eyepiece. It is lie on the fe, focal length of the focus of the eyepiece. So the image is formed at the infinity. So me equals to, we can write only 1 d plus d by fe, not 1 plus is there. Already we discussed in a simple microscope what happened if the image is formed at infinity. So m equals to what we can write, l by f0 into d by fe. So this is one, this is a very important, this type of numericals will come. Okay, so try to in your home, if you have any problem, please let me know. Okay, inform me or write in a comment box, ma'am, this expression I will not under, this numerical I did not understand, so I will explain that one also. Solution also given. Now comes to the next optical instrument, that is telescope. So telescope, it is an optical device which enable us to see distant object clearly, very far object clearly. It provides angular magnification of the distant object. There are two types of telescope. One is a refracting telescope, another one is a reflecting telescope. Refracting telescope, the it makes the lenses view distant object. That's why these are the two types. One is the astronomical telescope, another one is a terrestrial telescope. Astronomical telescope is used to see the heavenly bodies like sun, stars, planet. The final image is formed is inverted uh, one, which is the immaterial in case of heavenly bodies because they having the round shape. If they will if they will be the inverted, then also no change is there. And the terrestrial telescope, it is used to see the distant object on the surface of the earth. That's why the image is formed the erect terrestrial telescope. This is the types of refracting telescope, but this one is not included in your syllabus. Reflecting telescope, this is another one type of telescope. It is used for converging mirrors to view to distant object. For example, Newtonian telescope, Cassegrain telescope. These are the example of reflecting telescope. Astronomical telescope, it is a refracting type telescope used to see heavenly bodies like star, planets, satellites. It is consist with two lenses just opposite of the compound microscope. Here also we use two lenses, convex lenses. One is a objective lens, one is a eyepiece. But whatever the condition, that objective lens in case of a compound microscope is shorter aperture, short focal length, and the eyepiece will be the larger aperture and the focal length is greater than the objective. Here just opposite. The objective which has a large aperture and the eyepiece which has a small aperture and the small focal length, but this case the focal length of the objective is larger than the eyepiece. You see in this figure also. So we can, if we adjust like normal adjusting the telescope, the final image is formed at the infinity. Final image, this is a diagram for the image is formed at the infinity. And if we want to find out the magnifying power of a telescope, it is defined as the ratio of the angle subtended by the eye at the final image formed at the least distance of distinct vision to the angle subtended at the eye by the object at infinity when seen directly. That is a definition of magnifying power. So the m equals to beta by alpha h by fe into f0 by, the proof is not here, just you remember this one, that is equals to f0 by fe, f0 by fe. This is the magnification power in normal adjustment or when the object is at infinity. Now when the final image is formed at a least distance of distant vision from the eye, this is the ray diagram for that. Whenever the object image is formed at a least distance of distant vision, and the magnification will be this one. You just remember this is the proof is not included in your syllabus. M equals to minus f0 by fe 1 plus fe by d. So here first the this one is the object is at infinity, so the image is formed at focus of the eyepiece. Okay, that a dash b dash. Now this a dash b dash will be behaves like a simple microscope, so it will form a virtual image, erect image a double dash b double dash at a distance of distant vision. We adjust the lenses that in such a way that it will form at that least distance of distant vision. Clear? Reflecting types, and the first reflecting telescope is set up by the Newton in 1668. It consists with a large concave mirror of large focal length as the objective and made of an alloy of copper and tin. So whenever a beam of light from the distant object is incident on the objective, before the rays are focused at F, a plane mirror inclined at 45 degrees intercepts them and turns them towards an eyepiece adjusted perpendicular to the axis of the instrument. The eyepiece form a highly magnified virtual erect and distant object. Okay, this is the diagram for reflecting telescope. Okay, and the magnification m equals to f0 by fe, that is equals to f means r by 2, r by 2 divided by fe for the final image form at infinity, and the final above one, the whenever the final image is formed at this distance of distant vision, f0 by fe, that is equals to 1 plus fe by d. These are the two expression you have to remember. Derivation is not included in your syllabus. Now, the advantages of reflecting type telescope over the refracting telescope. There are many advantages. A concave mirror of large aperture has high gathering power and absorb very less amount of light than the lenses of large apertures. The final image formed in the reflecting telescope is very bright, so even very distant or faint star can be easily viewed. The use of the paraboidal mirror, you see that the diagram, paraboidal mirror reduces the spherical aberration. One drawback, the phenomenon of the formation of non-point and blurred image of a point. Another few things is it also, as the objective of in a mirror and not a lens, it is free from the chromatic aberration. Chromatic aberration means forms of colored image of a white object, because we know that the white color is consist with a seven color of light, that sometimes it will, whatever the image is formed, it will be colorful, it is not hazy. So that is a chromatic aberration. Because here we use the mirror, not a lens, so it is free from the chromatic aberration. Uh, Another one, a lens of large aperture tends to be very heavy, therefore difficult to make and support by its edges. On the other hand, a mirror of equivalent optical quality weighs very less and can be supported over entire back surfaces. Due to the large aperture, the mirror of the mirror used, the reflecting telescope has high resolving power. High resolving power. These are the advantages of reflecting type telescope over refracting telescope. The largest telescope in India, it is in Tamil Nadu. It is a reflecting type telescope. Another one also be used by Indian Institute of Astrophysics, that is Bangalore. Okay, so this all about the optical instruments. So if you have any problem, please write in a comment box. Tata, bye bye, have a nice day, stay safe, stay in your home, bye.